Hi, good afternoon, everyone. My name is Ted, and that's my colleague, Tang. We are from the Cognitive Open Tech Group, IBM Silicon Valley Lab. What we do in our group is we contribute to open source projects, and TensorFlow is one of the projects that we are currently working on. So we are interested in Bazel because it is the build tool for TensorFlow. So we are looking for ways to improve Bazel. So today our talk will be about improving the usability of remote caching. There you go. So in a talk yesterday, Stephen already talked about what Bazel remote caching is, so we're not going to talk more detail about it. For those who don't know, it's basically a cache server for Bazel to store or download the build output. So when other Bazel user can just who are building the same thing can just download it without building from scratch again. So today in our talk, we will focus more on our use case and also the current options for installing a Bazel remote cache. And in addition to that, we will show you two other ways of building or implementing your own Bazel remote cache server using Node.js and IBM HTTP server. And then finally, we will talk about cache storage management and also potential areas to improve Bazel remote cache. Okay, let's start. So we built the community version of TensorFlow for IBM Power. So this is our workflow. Basically, we have Jenkins jobs running on Power CI. The Power CI is hosted by Oregon State University, and the Jenkins monitors the TensorFlow GitHub. So whenever there's a change, it pulls down the new code and spin up a container from an IBM Power system and build the TensorFlow. And at the same time, it's reading and writing to a remote cache we set up. Since it's running inside container, so the TensorFlow is built every time from scratch. Before we had the remote cache set up, it was taking anywhere from 45 minutes to 1 hour. And after we set up a remote cache, it took only 5 minutes. So the remote cache saved us a lot of time. Here is a typical use case from Jacob Buchgraber presentation earlier this year, FOSDEM. He mentioned what a typical use case of Bazel remote caching is. Basically, you have your CI, and then you have a bunch of developers who is creating PR. Whenever there's a PR, the CI system builds the PR, and then at the same time also populating the remote cache. In his example, he says he used Nginx. The developers comes in and downloads the new the master, and then build on their local machine can directly download the cache and they don't need to build from scratch, so they will save time. So what are the current options for the Bazel remote cache server? On the Bazel side, they provide you with 3 options. The first one is Nginx. It's a popular web server. You can enable the put and get method using WebDev module. The second one is Bazel remote cache. This is also written by Jacob. It's written in Go, and you can run it with Docker. It provides cache management policy using LRU, which can clean up your old cache based on the last access date of the file. The third one is Google Cloud Storage. Obviously, if you run your CI system on Google Cloud, this would be a good choice for you. It also has object life cycle management, so for you to clean up your old caches. So before we show you how to implement your own Bazel remote cache, let's talk about web dev. So what is web dev? Basically, it's a HTTP extension. It lets client to perform remote web content authoring operations. Basically, it turns your web server into a file server. It provides additional verbs, copy, lock, unlock, and so on top of the existing HTTP verbs. Many web servers already support this extension. For example, Nginx, Apache, IBM HTTP, Microsoft IIS, and so on. So you can directly download the module and set it up. We also found Node.js also has the web dev module. So why would you need other options for your remote cache server? Obviously, if you already have, let's say, Nginx or Apache or something else or Node.js running on your current infrastructure, you can just directly reuse them. It's always useful to have those additional options. Okay, so let's first talk about how can you implement your own remote cache using Node.js. So we built this image from a Docker-based image, Node 10.11. Basically, you need two modules. First one is Express. Second one is js.dev. We will show you the code a little bit. It's in our GitHub. We'll show you the link to the GitHub later. So let me just quickly go over the code. So the way you do it is very simple. First, you need to import the Express module. And then you're going to import the JS.dev module. The JS.dev is actually the web dev. And then you will create a JS.dev object called dev handler. Inside the handler, you can set up where you will store your cache on the file system. In this case, it is saved under data/cache inside the current Node.js folder, project root folder. The next, you can create a Express middleware using app.use. And then inside this middleware, you'll set up a filter for the request. So whenever the request coming in with /cache, it will pass to the dev handler and do the dev handler will process the request for you. So if it's not cache, it'll just continue next. And then you can also set up other middleware, the apt-get for the root. If it's not cache, you can send a OK or something like that. For example, if it's a root and we just send OK, you can say something else. And then in the end, it's basically we start this Node.js app on a port 3000. So the second option we tried is using IBM HTTP server. The IBM HTTP server is basically Apache HTTP server underneath. So the same option can apply to either Apache or IBM HTTP server. So basically, you need to enable two modules. First one would be the mod dev, and the second one is the mod dev fs module. The way you enable this module should come installed with most Apache distribution. The way you can enable it is go to the httpd.conf, and then in there you should specify the lock file, and also you can specify where to store. In our case, it's var.www cache to store the cache. And then you're going to say dev on. This is how you turn on those two modules. And then you can, if you don't want people to browse your cache directory, you can say directory index disabled. And then the next, basically it only allow get, put, and delete verbs for requests for everybody. Notice in our sample implementation, we don't provide any cache management capability. You'd have to implement your own policy to clean up your cache. So here is the code, the GitHub link to the code, the two additional implementation we just showed you. If you want to modify or extend it, you can go to our GitHub. Or if you just want to download or run it quickly, you can just do docker pull and then docker run. This should start those servers real quick. Okay, so next I'm going to pass to my colleague Ton for him to talk about potential areas to improve Bazel remote cache management.
Thank you, Ted. All right, so next we will share a little bit about our experience with the remote cache, in our particular case, the CI build for TensorFlow. So the remote cache is specifically designed for the Bazel build. So it's helped to look under the hood a little bit and see what's going on. So you have this action that takes some source input along with some environment variable, the command line, and so on, and produce some output, right? So when we do the action again, then we'll just look at the anything that changed. If nothing changed, then we don't have to repeat the action, and we can use the output. So the way the cache track these change is by hashing all the input, everything on input, and then it also hash the content of the output. So that's how we track and change. So then the implementation for the cache basically just have two directory, one for the action cache, it's called the action cache, and one for the output, it's called the content addressable store or cache. Right? So in the action cache, we just have a bunch of files that has the hash as a name, and the content of the file point to the output for that action. The directory for the cache, again, she have a bunch of files that basically is the output of the build, and the name of the file are the hash of the content. So with the way we use the hashing as a name, then it allows us to hold output from all the build in the same cache. So that's how it works, right? So for that, we have several scenarios that could happen. So these are the a series of HTTP message to the remote cache server. The first scenario is that you have a hit on the action. So that means you look up on the action cache, you found a file there with that hash name. So that means that from the last build it hasn't changed. So then you just read out that file, and then you can find all the output build, the build output from that action. Then you just read those and use them. So that's a good case. The second case is when you have a miss on action, you try to read it and it's not there. So it could mean that something has changed since last build. So that caused the hash name to change. Or it could also mean that it got deleted. We can clean up the cache and it's gone. So in that case, you just have to redo the action. And then here you see that the Bazel build server would repeat the action and then put back the output, the build to the cache. So the third case is when you have a hit on the action and it's good, so you start reading the build output, then you find that some are not there anymore. And again, that's probably because it got cleaned up and got deleted. So then you have no option but just to go back and repeat the build and put back the content. So those are the potential scenarios that we can get. So with that, what kind of behavior we can expect out of the cache? So we see that all the build keep different version of the output in the cache. You could have duplicate write to the same output, but the content never change. So what it means is that the cache is going to constantly grow in size. with our TensorFlow build, we see that it can grow from 0 to 137 gig in just about 10 build. So it grew pretty quickly. If the cache is infinite, then the problem, you just keep filling up the cache. But of course, we don't have infinite cache. We have finite cache, so we have to have some kind of policy to manage the space. But the good thing is that whatever you decide to do, it only affects the performance. It doesn't affect the correctness of your build. So one thing we want to point out is that the Bazel side mentioned about garbage collection, but at least in our opinion, it's not quite garbage collection. Which GC, then typically you have a pointer so that you can track down and see what objects are not reachable anymore. Then you know it's safe to delete those objects. But in this case, a build output, even though it might be old, it's always possible that someone can kick off an old build and try to use that output. So it's more of a case of deciding what to kick out so that it minimizes the impact on your performance. Okay. Wrong one. All right. So what we did here is that we collect some data from our CI build. So in this experiment, we did a number of consecutive builds of TensorFlow, 7 builds altogether, and they just one follow one after. We kick off the build every 6 hours, 6 to 8 hours or so. So it's just pick up everything that got committed during that time frame. The build is done by within a new container each time. And this is how TensorFlow is built. And we use the Bazel remote cache from Jacob Buchgraber. And we collect the log output from the server, and we also look at the content of the cache itself to see what's going on. So on this chart here, we overlay two charts. The blue bar is the hit rate on the action cache, right? And the orange line is the build time for the TensorFlow build. So we see here we have an inverse relationship between the two. When the hit is low, then build time is high, and versus when the hit rate is high, then build time is low. So that's good. So that it's working. It shows that the remote cache is working just as expected. So on the bottom line, I show the number there on the x-axis show the number of files that are changed between each build. So for instance, the first line means that 99 files will change. So this kind of gives us an observation on the how sensitive the cache is versus the build in the TensorFlow. TensorFlow has about 13,000 files. So 99 files is about 0.7% of that repo. We saw that just that small change caused a drop of 40% drop in the action cache. So we're not sure whether this just means that we in the TensorFlow the script over specify the dependency or not, but that could be the case. Of course, if we can really clean it up, then it should give you more benefit in the caching. But of course, going back to analyze the script to clean up the dependencies is a lot of work. In the talk this morning, Ove mentioned about some tool to manage or generate the dependency, so that could be a big help there. Okay. So next, we look at the volume of the traffic to the remote cache. So here we did the y-axis show a range from 15 gig to 70 gig, and the volume stayed pretty much constant about 16 gig, and this is the volume that gets transferred back and forth from the cache every time. So everything is either read from the cache or written to the cache. So this does show that even if you have 100% hit on the action cache, the lower bound on the build time is still the time it takes to transfer 16 gig over the network. Right. So that means that you want a pretty good network for your remote cache. Okay. So here's the count of the message to and from the remote cache. So the blue line there shows the total count, and we're seeing that there's about 90,000 messages per build. So a fair amount number of messages. Now, what's one peculiar behavior we're seeing is that is what's showing up in the orange bar chart there. So these are the number of messages that has zero content. So the size, what's been written to is empty. They're all written to being written to a file in a cache that has a zero size. So we don't know. We have to look further to see what is coming from. We're not sure whether it's just the behavior of the way the basic script is written, or whether it's is intended to work this way. But if we can avoid this, then potentially we can save a fair number of message into the cache, about 30%. Okay, so this show the something else we noticed. So this chart will show the number of write to the cache. So this means that these are all the update to the cache for the output build of that, for the output build. Okay, so the blue chart show the total number of write, and the orange line show the unique file being written for among these write. Right? So remember that the name of the file in the cache is from the hash of the content. So if you want to write to the same file again, it's never necessary. And the gap between the blue chart and the orange chart show the number of these duplicate write. So we trace back some of these write, and they actually come from different actions. So these are real legitimate write. But it does show that if there's a way to detect those write and not repeat them, then that could potentially be a saving as well. And if we can do this from the side of the Bazel build server, then we can just avoid all these write to the cache. Right? So that could be another potential saving. Right. So let's talk about how we manage the storage. We saw that the volume to the cache is pretty constant, and the trade-off here is basically between reading from the cache and repeating the action, carrying out the completion again. So if you decide on the policy for evicting something in the cache, that's something you want to think about. How much time, how much effort would take to repeat that action. The Bazel remote cache implement the least recently used policy. So when you have to delete something, you just look for a file that hasn't been read for a while. So it worked pretty well. In our CI build, it worked quite well, in fact, because our build constantly move forward. So if something hasn't been accessed for over one build, then it probably has been updated but with a later version. So it's pretty safe to just delete it. But if we are sharing the build output among many people, then potentially someone could be reusing of some of the old build output. So in that case, maybe it might be better to evict a file based on how frequently it's used. So we need to have a way to count the number of access, right? So then when we need to delete something, then we'll just find something that's not used frequently. Another way to decide is to look at the size. So here's a trade-off between deleting a few large files versus deleting a lot of small files. So if we delete a few large files, then that should improve the hit rate on the cache. Right? Another approach is to look at the effort it takes to compute, to carry out the action. So with that, it might make sense to keep around something that takes a long time to compute, and then kick out something that is easy to compute. Right? And a variation of that is to look at the content of the file by looking at the file extension, like for instance a .o file, .d file, or .jar file, and decide based on that. So maybe an archive file is easier to produce, because mostly it's just stuck in a lot of output that's already been produced. So these are different policies that we can think about. Now, to implement this policy, we have a couple of options. We know that the Bazel remote cache already implement the RU code, so it should be straightforward to go in there and extend it. to add the other policy and give that as option to the user. For the HTTP server, they don't have a good way to run something in the background. So it may make more sense to have a separate process you just run as a daemon in your cache server, and it just monitor the directory and then just go in and clean up file based on your policy. Now, if we just want to evaluate the different policy without having to implement them and run on different build, then we found that the Bazel remote cache does put out a nice log of all the message, so we can use those log to run trace-driven simulation, just like typically done with cache. So that should give you a pretty good estimate for the different policy, and if you can collect the time for each of those action, then potentially you can estimate the build time as well. Okay. So that's our talk. To recap, we described some additional option for deploying the remote cache, using the Node.js and using the HTTP server. These codes are available if you want to use them. We did not implement the secure access, but that's something that if there's interest, we can add that as well. It shouldn't take too much work. And or if anyone would like to do a pull request, we welcome that as well. And in my part, I show some data that potentially could point to some technique we can potentially improve the cache performance. And we look at some of the potential policy for managing the storage. Okay. That's our talk. If any question, we'd like to